In this another lecture of electronic devices, we are going to cover diode capacitance and junction diode switching time. So there are two types of diode capacitance. First is space charge or transition capacitance and second is diffusion capacitance. So first we cover space charge or transition capacitance. So if we talk about a reverse bias which causes majority carriers to move away from the junction, thereby uncovering more immovable charges, and the thickness of space charge layer at the junction increases with reverse voltage. So this increase in uncovered charge with applied voltage may be considered a capacitance effect. So we can define an incremental capacitance CT by CT equal to dq upon dV, where dq is the increase in charge caused by change dV in the voltage. It follows from this definition that the change in voltage dV in time dt will result in current I equal to dq upon dt, that can be also given by I equal to Ct dV upon dt. So therefore a knowledge of Ct is important in considering a diode or a transistor as a circuit element. So the quantity Ct is referred to as transition region, space charge, barrier or diffusion region capacitance. So as this capacitance Ct is not constant, it depends upon the magnitude of reverse voltage. So it is for this reason Ct is defined by equation I equal to Ct dV upon dt rather than the ratio of dq upon dV. So to understand the effect of space charge or transition capacitance in diode, we first cover a step graded junction. So consider a junction in which there is an abrupt change of acceptor ions on the one side to the donor ions on the other side. Such junction is formed experimentally, for example by placing indium, which is trivalent, against n-type germanium and heating the combination to a high temperature for a short time. So some of the indium dissolves into the germanium to change the germanium from N to P type at the junction. So such step graded junction is called an alloy or fusion or a junction. So a step graded junction is also found between emitter and base of integrated transistor. So it is not necessary that concentration Na of acceptor ions is equal to concentration Nd of donor impurities. So as a matter of fact, it is often advantageous to have an unsymmetrical junction. So in this figure, it shows that the charge density as a function of distance from an alloy junction in which acceptor impurities density is assumed to much larger than donor concentration. Since the net charge must be 0, then Na dot Wp equal to Nd dot Wn. So if Na is very greater than Nd and Wp is very smaller than Wn, which we consider as W, the relationship between potential and the charge density is given by Poisson equation. So we already know the Poisson equation, that is d square V upon ds square equal to minus rho upon epsilon. So rho is replaced by minus q dot Nd, as Na is very greater than Nd. So integrating this equation with the help of boundary condition, so from this figure you can see that at x equal to Wn equal to minus dV upon ds equal to 0, at x equal to Wn, that is around, we are equating it to W, so dV upon dx equal to minus q and d upon epsilon x minus W, so which can be equated using Poisson equation, that is equal to minus of E. So neglecting the small potential drop across the Wp, we may arbitrarily choose V equal to 0 at x equal to 0. So integrating this equation again subject to this condition, we obtain V equal to minus q and d upon twice epsilon x square minus twice Wx. So the linear variation in field density and the quadratic dependence of the potential upon the distance are plotted in figures C and D. So at x equal to W, V equal to Vj, that is junction or barrier potential. So thus this V is equal to Vj at x equal to w. So we are putting x equal to w in this equation. So we get Vj equal to q and d dot w square upon twice epsilon. So where Vj is given by from this equation, from this figure, such that Vj equal to V0 minus Vd. So where Vd is the negative number for the applied reverse bias and V0 is the contact potential. So this equation confirms that the thickness of the depletion layer increases with applied reverse voltage. So if we put this equation Vj into this equation, then we can see that W is varies as under root of Vj, or we can say under root of V0 minus Vd. So this is our conclusion. So if we talk about a step graded junction, if A is the area of the junction and charge in distance W is given by Q, then Q can be calculated as Q dot ND dot W dot A from figure B. So the transition capacitance Ct, which is the ratio of dq upon dvd, that is the reverse applied bias. So if we put the value of q in this equation, we get q and dA dot dw upon dvj. So we know that vj equal to q and d dot w square upon twice epsilon. So from this equation, we can get dw upon dvj by differentiating is equal to epsilon upon q and dw. So hence if we put this value into this equation, then we get Ct equal to A epsilon upon W. So this relationship is very interesting because this formula is exactly the expression which is obtained for parallel plate capacitor, which is having area A and plate separation W and containing the material permittivity epsilon. So if the concentration Na is not neglected, the above results are modified only slightly, as we are talking about the total weight. So the total weight, which is the total space charge weight, and in this equation 1 upon Nd is replaced by total concentration, that is 1 upon Na plus 1 upon Nd. So this equation can be modified by replacing 1 upon Nd through this expression. So we can calculate the total barrier potential inside step graded junction. So now we are going to understand the space charge capacitance inside a linearly graded junction. So if we talk about a linearly graded junction, which is a second form of junction and is obtained by drawing a single crystal from a melt germanium, whose type is changed during the drawing process by adding first p-type and then n-type impurities. So there is a grading of impurities inside the crystal. So linearly graded junction is also formed between the collector and base junction of the integrated transistor. So for such a junction, the charge density varies gradually or almost linearly, so which can be shown in this figure, which shows us that the charge density variation versus distance at linearly graded PN junction. So if analysis similar to step junction is carried out for such a junction, then we can obtain Ct similar to A epsilon upon W. So this equation is also valid for linearly graded junction, where W is equals to the total width of the space charge layer. So in this step graded junction, we have seen that W varies as under root of Vj, but for linearly graded junction, it is seen that W varies as Vj power of 1/3. So for linearly graded junction, the width is proportional to Vj power 1/3. So what is the use of space charge capacitance? So we used its phenomena in varactor diodes. So we observed from above equations that the barrier capacitance is not a constant but varies with applied voltage. So the larger the reverse voltage, the larger is the space width W. So hence the smaller the capacitance Ct. Similarly, for an increase in forward bias, that is Vd positive, W decreases and Ct increases. So this variation can be seen in this figure of two typical diodes. Their typical barrier capacitance variation with reverse voltage for silicon diode 1N914 and 916 is solved. So you can see here that for an increase in forward bias, VD positive, W decreases and CT increases. So voltage variable capacitance of PN junction diode biased in reverse direction is useful in number of circuits. So one of these applications in voltage tuning of LC resonant circuit, other applications including self-balancing bridge circuits and special type of amplifiers called parametric amplifiers. So diode made for especially for this purpose, which are based on the voltage variable capacitance, are called varactor, varicap or volta caps. So circuit model for varactor diode and the reverse bias is shown here in this figure. So the resistance Rs represents the body series resistance of the diode. So typical value of CD and Rs is 20 picofarad and 8.5 ohm at reverse bias of 4 volt. So the reverse diode resistance RR shunting CD is very large, it is around of 1 mega ohm and hence is usually neglected. So in circuit intended for use with fast waveforms or at high frequencies, it is required that transition capacitance be as small as possible. Next category of capacitance is diffusion capacitance. So for a forward bias, a capacitance which is much larger than the transition capacitance CT comes into play. So the origin of this larger capacitance lies in the injected charge stored near the junction outside the transition region. So it is convenient to introduce an incremental capacitance defined as the rate of change of injected charge with voltage, that is called diffusion or storage capacitance CD. So if we talk about static derivation of CD, so CD can be given by dq upon dv, or we can write it as tau di upon dv, or tau dot g, or tau upon r, where diode incremental resistance is given by G equal to di upon dv. So substituting the expression for diode incremental resistance R equal to 1 by G, so we can write CD equal to tau I upon eta Vt. So hence we see that the diffusion capacitance is proportional to the current I. So in the derivation we assume that the diode current I is due to holes only. So if this assumption is not satisfied and gives the diffusion capacitance CD due to holes only, and similar expression can be obtained for diffusion capacitance CD due to electrons. The total diffusion capacitance then be obtained as a sum of CDP and CDN. Total diffusion capacitance is the summation of due to diffusion capacitance of holes and due to diffusion capacitance of electrons. So for a reverse bias, G is very small and CD may be neglected compared to CD. So for forward current, on the other hand, CD is usually much larger than CD. So in this slide, we have covered space charge capacitance and diffusion capacitance. Thank you.